invitation. For the invitation to this colloquium and yeah, also for the introduction. We are talking on a topic which Eva and I started a few years ago together with Lorenzo and Renaud, who had been postdocs with us for some time in Bonn. And it's a topic which is a little bit out of our mainstream research. So you might know, or many of you might know, that my main focus is on metric measure space and synthetic Ritchie bounds. There is, of course, a link. We are very fascinated of this idea to construct kind of universally random metric measure spaces. But at the moment, of course, this is far away from any Ritchie bound geometries which we construct. So, yeah, what are we talking about? Let me start a little bit more with an heuristic, and I will go with a heuristic for quite some time, and then I will mention a moment when we go when we are more specific. So the original goal, which is behind this, is an idea which pops up in various fields of mathematics and physics, mathematical physics, that one would like to take an average over the set of all manifolds of a certain dimension or of certain subsets of set of all manifolds. This, in general, of course, is not really a good aim. This is too much to ask for. But what is more promising is we can fix a reference space, and then we ask for an average over all these manifolds, which are weighted manifolds with respect to the given reference manifold. Now you take your manifold with a metric tensor, and then you change this metric tensor by a function, and then averaging over these manifolds means just you have a measure on these functions. And to avoid complete arbitrariness, we would impose two conditions on such a random measure. First of all, we want that this random measure is conformally invariant in the following sense: if you have one manifold here, and if you have one manifold with two different metric tensors which are weighted versions of each other, then the distribution should be the same. Anyway, we regard this conformal class, and the measure on this function's h should not depend whether you choose g to start with or always some weighted version. This is one restriction. The other restriction is if you have two manifolds, m and n prime, and if you have an isometry between these two manifolds, then this isometry should map these random functions here onto random functions there. In particular, in dimension 2, this is very important because in dimension 2, you have this strong result that you can map every simply connected Riemannian manifold on a standard manifold, and the same with higher genus objects. So this, of course, is extremely powerful in dimension 2 or extremely restrictive. But it turns out that even in higher dimensions, these two conditions will rule out, will be so restrictive that essentially there is only one measure which survives. Okay, I have to be a little bit more careful in the sequel, but kind of non-standard fact is that this also is a very, very interesting question in dimension different from 2. And in all what we construct in the sequel, the second property is in some sense given for granted. All our constructions are in such a way that we have this isometric mapping property. We focus then more on this property, this conformal transformation, and in the sequel we fix therefore one manifold forever. So this is given, but our constructions are always that in such a way that the second property is fulfilled, but not mentioned specifically. I was a little bit too quick in saying that there is essentially one solution. There is one solution if we restrict our measures to be Gaussian measures of this form. So we typically want that such a distribution on functions is a Gaussian field, or in our case at least, this is the starting point. This is where we begin with. We would like to define the distribution of its functions heuristically as a uniform distribution on functions weighted by some energy functional, some quadratic functional. And of course, you know, this is not really a strict, rigorous definition, because there does not exist a uniform distribution of functions. And as a consequence, if you try to approximate this, the normalizing constant will explode. But as a guiding interpretation, this you should have in mind. So this is the way how we construct our measure, giving a rigorous meaning to that. So this energy is a bilinear form. It has a generator A, and the rigorous definition uses the inverse operator and the dual energy functional. So this is then the Bochner-Mindlers theorem. You write down the characteristic function for distributions in terms of this dual energy. So where this E is, for instance, in classical cases, the Dirichlet energy. This is in classical cases the green energy. So you just invert this operator. The typical case is that A is a Laplacian, and now it's a green operator. And you have here objects which are well defined. You have the inverse of a Laplacian, the green kernel. I make this more precise in physical. And with this inverse operator in its kernel, it more or less means that we construct fields which have mean value 0, which are centered for each x. The expectation of h of x is 0, and the covariance is given by this kernel. This is a little bit sloppy because it turns out that these fields which we construct are not functions. So one should regard this with care. But as a guideline, this is indeed what we do. We have an energy functional, and with the inverse generator, we have a kernel, and the kernel determines the covariance of these fields. And our conformal invariance property for these distributions then amount to a conformal invariance of this energy. Yeah, naively, we pretend that this measure is conformally invariant, this non-existing measure. And then this should be conformally invariant, or let's say this is invariant under translations, which would be the translations. The conformal weights here would mean this is a translation here. So this measure should be, this heuristic non-existent measure should be shift invariant on this space. And nevertheless, what we ask ourselves, what are the energies which are conformally invariant? So we want that the energy in terms of a metric tensor does not change on a given manifold if we change the metric tensor. And in dimension 2, this is a celebrated property of a Dirichlet energy. And we come back to this just on the next slide. Of course, the gradient changes if we go to a weighted space, and the volume changes, but in dimension 2, these two effects cancel. So this is a good choice. And this has as a consequence that with this heuristic definition here, in dimension 2, you obtain important concept, namely the Gaussian free field. And this Gaussian free field is conformally invariant. This is one of a very important property. And therefore, all these objects which are constructed out of a Gaussian free field are conformally invariant. So this is the Liouville quantum gravity measure, where roughly speaking, you take exponentials of these fields and regard this then as weighted measures. The delicate issue here is also in dimension 2, this Gaussian free field does not produce functions, this produces distributions, not really super bad distributions, but distributions which are no longer in L2, but only in negative Sobolev spaces. And therefore, exponentiating these distributions is not really a trivial aspect, and this requires normalization techniques, which I will present, or Eva will present then in our approach with a higher dimensional construction, which mimics just the two-dimensional case. So, and why do we subtract here the expectation? Okay, because this is a kind of exponential martingale. Yeah? If we put in a regularization parameter here for the field, we also would have this parameter there. And then in this regularization parameter, this is a martingale. This is a martingale, and this exponential stuff is then a martingale if we subtract 1/2 of expectation squared of this guy, or 1/2 of the variance. And therefore, this is the first step. The second step, which has to be done, is an approximation. And then this gives a well-defined object. We will come to this in the second part. But this Gaussian free field is also closely linked to many other important conformally invariant random objects in 2 dimensions, namely the SLEs. So level sets of a Gaussian free field are described in terms of SLEs. And it is also very, very intimately linked to the Brownian map constructed by Le Gall and Mirmont. So it's the universal scaling limit of planar random graphs. And it turns out that this is, so this Brownian map can be regarded as a random metric measure space, and this is the measure on this random metric measure space. This is the situation in dimension 2. There are hundreds of papers, very fascinating results, and only very, very few results in dimension different from 2. Of course, the construction of a random field is also well known in higher dimensions if you speak of log correlated fields, but not much, almost nothing is known concerning conformally invariant objects in higher dimensions. And okay, I have added a small excursion now to give a meaning. How can we give a meaning to this in dimension 1? Okay, this is maybe boring to those who know about the Gaussian free field. For those who are not familiar with that, you can consider this as an easy attempt to make you a little bit comfortable with this concept. So now we switch to dimension 1, and we again look on this heuristic interpretation. We again take the Dirichlet energy here as a scaling factor, and we take this heuristic uniform distribution on continuous functions. Again, of course, this does not exist, but you can give a rigorous meaning to that, and this will be, at the end of the day, the Wiener measure. So if you, let's say, restrict your space to 0, 1, then it's the Wiener measure with time running from 0 to 1, and for convenience, let's say at 0, we start at 0. And how can you see that the Wiener measure is a good rigorous construction for this heuristic? Replace this heuristic by a discretization. And discretization means you have your interval 0 to 1, you make a partition of the time, and then at each time instant, you only have to sample the value of a function at this time instant. So instead of sampling the continuous function, you sample only the values of these functions at this n time instances. So you have to sample these function values, and you do this indeed with a Lebesgue measure. Now you say the H1 is uniformly distributed on the real line, whatever uniformly distributed means, but the distribution is a Lebesgue measure. And the n-dimensional vector is just distributed with the n-dimensional Lebesgue measure. And then you give a rate function to this in terms of a discrete Dirichlet energy. Now you have your discrete values, you interpolate them by a piecewise linear curve and calculate the Dirichlet energy for this. And then you choose the appropriate normalization constant in order that this is a probability measure. And you see, if you write down this formula explicitly, this is exactly the Chapman-Kolmogorov formula for the Brownian motion given in terms of a heat current at this time instances. Right? If you make the discretization of this Dirichlet energy, take here uniform distribution for this HI in the sense of Lebesgue measure on this n-dimensional space. Then you have a discrete version of this guy with an appropriate normalization constant. And you all know that this Chapman-Kolmogorov representation, if n goes to infinity, gives a unique limit point, namely the Wiener measure. Another way is you can construct this measure also in a way where you look on the generator of this energy, which is the Laplacian. And this is a point which we will also use later on. We ask for the generator of this energy for its eigenfunctions and eigenvalues. So you have the eigenfunctions psi j, the eigenvalues nu j for this directly Laplacian on 0, 1. And you multiply the eigenfunctions by IID normal variables, scale it with the inverse square roots of eigenvalues, and then this is an approximation of this continuous function. So if you let run this sum only from j to capital K, let's say, this is of course a nice infinity function as a function of x. So this has the x dependence, this has the omega dependence. And if you write down this explicitly, you see the eigenfunctions of the Laplacian are the sine functions, the eigenvalues are j squared times something, the inverse square root is 1 over j, and this is exactly a formula already proven by Wiener for explicit construction of boundary motion. This construction leads to a well-known Brownian motion, which is a measure on functions of class C1/2 minus epsilon. So they are a little bit worse than Hölder 1/2 regular. This is the regularity in dimension 1. The higher you go in dimension, the worse is the regularity. In dimension 2, you have here something like C0 minus epsilon. More precisely, you construct, just mimicking this construction, you end up with distributions in Sobolev space H minus epsilon for every epsilon. So just do the same in two-dimensional space, make a discretization, just take a interpolation of piecewise linear functions. Yeah, you have these two-dimensional discretizations. When you have these head functions, you can calculate the Dirichlet energy. This gives one way to construct that. Or you take the two-dimensional Laplacian. On the square, for instance, the eigenbases are just sine functions, where here you have two pairs of functions, J1 and J2, and arguments x1 and x2, and then you have a similar representation. But you have a worse order of convergence, so it does not converge to functions, it converges only to distributions. This is the case in dimension 1 and in dimension 2. And now, what happens if we want to go to higher dimensions? So far we discussed this ansatz with the Dirichlet energy, but in dimension different from 2, the Dirichlet energy is no longer conformally invariant. Why is this the case? If you change the metric tensor from G to e to the 2 phi G, this means that you change the length to e to the phi times the original length. So the gradient becomes an e to the minus phi, and the volume are e to the n phi. Volume goes with factor n, length goes with factor 1, and there is a square, so you have an n minus 2. And this makes it clear that only in dimension 2 you have a conformal invariance for this Dirichlet energy, and in higher dimensions, but also in dimension 1, this is not conformally invariant. If you ask for conformal invariance, you can try it better. What you see here is the volume always goes with n, gradient goes with 1, gradient square with 2. So in dimension 4, we would be more successful perhaps with a Laplacian, because it essentially goes with 2 orders, and if we square it, it's 4 orders. But the Laplacian itself is not really going with the factor squared, but it also comes with low order terms. So if you calculate the energy in dimension 4, or if you start with this bi-Laplacian here, you see that the transformed energy looks similar, but it has this low order term. So this energy is essentially the same up to low order terms. Now, you make a reverse engineering. You want to get rid of these low order terms here. So you put low order terms there. And this means, okay, this is a not obvious task, but it's already solved by Panitz. And Panitz told us that the conformally invariant energy in dimension 4 is given by this formula. It's the Laplacian squared minus 2 times the Ricci of this vector fields plus 2/3 of the scalar curvature times the gradient squared. Times the constant. The constant is chosen for convenience as this number, but the conformal invariance, of course, does not depend on the choice of constant. But this is the only conformal invariant energy generated by a differential operator in dimension 4. So as the Dirichlet energy is the only conformal invariant energy in dimension 2. So in dimension 4, you have this bi-Laplacian, so the generators the bi-Laplacian plus low order terms. And in dimension n, it's essentially the Laplacian to the n-half. I have put it now on one side. You can make integration by parts. Then you see the generator is negative Laplacian to the n/2, which is an operator of order n, which sounds good, plus low order terms. So this is work by Graham, Chen, Mason, Sparling, on which we rely, which again says in even dimension, there is conformal invariant energy based on a differential operator, and only in even dimensions, and this is the unique conformal invariant energy with a generator being a differential operator. Namely, the generator is the negative Laplacian to the n/2 plus low order terms. The low order terms are specified uniquely, but it's quite horrible to write them down. So you cannot give an explicit formula. We have seen it in dimension 4. You can find formulas in dimension 6. Maybe also somebody calculated in dimension 8, but there is no general approach. There are some formula for specific manifolds. So if you have constant curvature, you can write down things in particular for the sphere and for hyperbolic spaces and so on. For convenience, we also choose the normalization constant here with a particular value. This is just to know that we have decided to have a particular choice. This is, of course, not a consequence of conformal invariance. This is just our choice. And now, for technical reasons, I have to introduce some notation. I already did some of his arguments in this heuristic part, namely inverting the Laplacian, but now I have to be a little bit more specific. What we are working on are compact closed manifolds, or manifolds without boundary, like the sphere, dimension 1, the circle, torus, things like that, quotients of hyperbolic spaces. But all these spaces are compact and they don't have boundaries. So the constant 1 is always in these spaces, and the constant 1, of course, always is Laplacian 0. So you cannot invert the Laplacian if you do not factor out the constants. And this is what we have to do. This is the so-called grounding. So we are mostly interested in functions u which have mean value 0, or distributions which paired with a constant 1 are 0. So all our function spaces have this circle here, which means these are functions where we factor out the constants. And then on this grounded Sobolev spaces, the Laplacian acts by decreasing the order by 2, and the inverse Laplacian is well defined, and it increases the order by 2. Now, this is just factoring out the constants. This is technical necessity. This is a very natural way how we should do it. And you know that no green function would exist on a compact space in dimensions, but modulo constants, we can write down this kernel. The kernel is no longer positive, of course, because also the kernel is then grounded. The kernel has, again, mean value 0 in each of its arguments. And what is also not clear is now that our energy is positive. Let me come back to this energy. So the energy is, of course, a positive or non-negative energy plus low order terms. And if we go back to this explicit formula of Connacht's, you see this is, of course, always non-negative, but these terms could produce negative value at the end of the day, and indeed this happens occasionally. In some cases, we can guarantee that the energy is always positive on all functions orthogonal with a constant, and this spaces we call admissible. And for talk today, I think it's enough to say that we have plenty of admissible spaces. Compact Einstein 4 manifolds. Let's focus on dimension 4. Compact Einstein manifolds with non-negative Ricci are admissible. And if you want to go to negative curvature, compact hyperbolic 4 manifolds are admissible if the spectral gap is large enough. And indeed, this is also the situation. If this is violated, we can construct manifolds which are non-admissible. But let us ignore this aspect for the moment. I think this is not the most important aspect. We have some ideas to overcome this restriction of admissibility. But at the moment, we restrict to admissible spaces.
Wow. Excuse me for the interruption. Very naive question. What does it mean, the Laplacian raised to a power? How do you interpret this?
You mean here, for instance?
Yes.
Okay, I would say the most easy way is if you want a compact space. The Laplacian has a compact spectrum. You have eigenfunctions, eigenvalues, and raising the Laplacian to a positive or negative power just means raising the eigenvalues to this power.
Okay, you keep
building a new operator just by writing down it into eigenbases.
Okay, thank you. I got it.
Now you don't even need a general spectral theorem. You can just write down this as a sum, acting on eigenfunctions with eigenvalues, and you raise the eigenvalues to this negative power.
Okay, thank you so much.
But Laplacian to the -1, this is the green operator in classical case. The only thing is we have to factor out the constant. Otherwise, there is no green term on a compact space because you cannot invert the constant 1. There is no function whose Laplacian is constant 1 on a compact space.
Okay.
And but the easiest way is with spectral calculus, discrete spectrum, and then you are done.
Thank you.
Yeah, and also this we should do here with this Panel's operator or copolar harmonic operator. We now take the inverse of an operator which we have defined before. So this is essentially the negative Laplacian to the power n/2, and now we invert it, so it's the negative Laplacian to the power negative n/2, which is essentially an iterated green operator. N-half iteration of a green operator. And in this case, it's of advantage that n is always even in our approach. This operator defines a bilinear form, and more precisely, this K turns out to be an integral operator, and it has an integral kernel, which is grounded, means the mean value in each of these variables vanishes, and it's symmetric. This is no surprise. But what is important, this kernel has a singularity at the diagonal, which is exactly negative logarithm of a distance. So there is no prefactor in front, and this is important, but this is achieved since we have chosen the constant in a specific way. Yeah? We have chosen this an here in front of this operator in order that now here we don't have a constant. And this property is important because later on this is really the crucial property in order to be able to apply this or to define this Liouville quantum gravity measures and multiplicative chaos concepts. So this is what is called log correlated. It means the kernel has a singularity which is exactly negative logarithm of a distance function. Close to the diagonal and outside it doesn't matter since we are on a compact space, it's bounded. And the second important property of its kernel, it's conformally invariant. Namely, if we change from G to G prime, the kernel is essentially the same up to a normalization, and the normalization is a function which depends only on one variable. Yeah, it's not a product space, but at each variable we subtract something, And this has to do with the fact that we want this kernel to be grounded with respect to the given volume measure. But if we change the metric, we also change the volume measure. So this was grounded with respect to G, but since we changed the volume now, this no longer has mean value series. So we have to subtract something, and these are just the mean values of this guy with respect to the new measure. But this is completely irrelevant if you want to construct a random field, because it has no joint dependence. So these are just decoration in some sense. And now we have two properties, and actually these are the two properties which are relevant for all the subsequent constructions. We need a log correlated kernel, and we need conformal invariant. And this was a kind of nice surprise that for these two properties, in some sense come together. To get conformal invariance, this is how we started with. It turned out we need an operator of order n. Because this is the only way we can achieve conformal invariance. And if we have a differential operator of order n, and if we choose the precise prefactor, then the kernel is logarithmic. If we would choose in dimension n, an operator, the kernel has always for order 1 over n minus k, where k is the order of an operator, and n is by dimension. And if k is n, it's not 0, the kernel is logarithmic. If a kernel would have a singularity which is really algebraic, we would have no chance to construct a Liouville quantum gravity measure. If a kernel is bounded, it would be completely easy. There would be no need for renormalization. So this is indeed the borderline case in the sense it's doable, but it's non-trivial. And this, of course, is then the challenge for every mathematician. You want something which is at the end doable, but it should not be too easy. So we start now to define rigorously these Gaussian fields, and we define them. I have presented in this heuristic introduction various fields, various definitions. The rigorous definition is we want fields parameterized by functions, and these functions could be in whatever function space. The largest is Sobolev space of negative order, but you also could start here with Sobolev space of positive order. There is a huge variety. This is the maximal space with which you can test your random fields, and you want that the covariance tested against functions u and v is this dual energy with respect to this inverse Panhard operator. And in a more heuristic way, this says, if you write down this really as integrals, this says that the expectation of hx, hy is k of xy, where k is the integral kernel for the inverse Panhard operator. This has to be treated with care. The rigorous meaning is here, but this is the intuitive interpretation you should have in mind. But care is needed because we will see that these h are not functions. And explicit construction is now again possible through the spectral calculus on our space. We have a compact space. We choose eigenbases, so eigenfunctions and eigenvalues for this Panhard operator. And we do the same as Wiener did for one-dimensional ground in motion. So we choose these eigenfunctions, which give the x dependence of our random field. We multiply them by standard normals, which give the omega dependence, and we rescale them by the inverse square roots of the eigenvalues of our Panhard operator. And yeah, the content of this theorem is this definition. I will make a little bit more explicit on the next slide how this has to be understood. This definition is meaningful, and it gives an explicit construction of a fields H which satisfies this condition. So this is the explicit construction of such random fields. It turns out that in any dimension, this is any even dimension, this is a field which is a little bit worse than functions. So it's in negative Sobolev spaces, and how should you consider this? So I have written this definition on the previous slide, and how do we interpret this sum? Let's start with a partial sum. So let's make the sum from 1 to L, where L is an integer. Then as a function of x, these are C infinity functions, yeah, because the eigenfunctions are smooth. You multiply them by noise parameters and scalar numbers. So this is a C infinity function on your given manifold. And as random variables, these are centered Gaussian random variables because these are centered Gaussian guys. And now if L goes to infinity, this object converges to this limit object in various ways, for instance, in L2 with respect to omega and in Sobolev space of negative order with respect to x. And we also have at the end of the day that each of these limit objects lies into Sobolev space. And another way of interpretation is you pair this random field with test functions. So you multiply this by test functions in whatever or distribution, Sobolev space, positive, negative order. This doesn't really matter that much. And then as a function of L, this is a martingale. And you get martingale convergence result to this limit object. And you can imagine the following: if you make this approximation with this parameter L, for small L, these are really the C infinity functions. You add more and more noise, so these functions get more and more rough. And the limit, yeah, you should get something which obviously is no longer a function. So depending on your discretization, you end up with a very singular object. But at the end of the day, of course, it's not possible to plot this because it's no longer a function. And since you have a distribution, it doesn't make sense to really speak of these images. What we also need then occasionally is what is called the ungrounded field. And this is also used by people in physics and so on. So far, we have discussed always grounded functions. So we have always requested that the mean value is 0. And roughly speaking, the idea of this ungrounding now is take a function, subtract its mean values, then it's ungrounded, then it's grounded, and then you add a parameter t randomly chosen on the real line. So the mean value is in some sense arbitrary on the real line. And this gives you the ungrounded field. Yeah? These are grounded functions, the functions of x and omega, distributed according to the measure which we have defined before. So this is a probability measure of the distribution of these grounded parts. And then you add a parameter t, which stands for the mean value. And the mean value has no constraints. So there is no reason why the mean value should be small or positive or negative or whatsoever. And this is a meaningful measure. It's no longer a probability measure, and therefore sometimes it has to be taken with care if you think of martingale convergence results and so on. This measure is really a measure, not a probability measure. And this measure is indeed what informally should be characterized by our initial formula. And you see here, if you think of eigenmodes, the constants are not scaled because the energy of a constant vanishes. So the constants really fluctuate from negative infinity to positive infinity. All functions which have energy, they are scaled down. And this is the meaning of this formula. And this is exactly given by this rigorous definition. Let me come to an important result, namely the grounded field is the ungrounded field, is conformally invariant. So if you have your compact manifold, if you make a change of a metric tensor, then the random field associated with this manifold is the same as for that. this is the nice formulation for ungrounded fields. If you go back to the grounded fields, okay, then this can no longer be true because this is a random distribution which is grounded. And also this should be a random distribution which is grounded. So at least if this H gives you some information for the H prime, you have to subtract the mean value, the spatial mean value of this H. And this is exactly what you do here. You start with a random field, you subtract the mean value with respect to the new measure, and then this gives you a random field with respect to the new metric. This looks a little bit more complicated. With an ungrounded, you have a complete easy representation that this is without any correction term conformally. Now, the final result which I want to present you is a discrete approximation. Now think of a particular example, namely the continuous torus, which we think of 0,1 to the power n, and the discrete torus, which is the lattice with lattice points in each direction and distance 1 over L, where L is an integer. And this has the advantage that on the discrete lattice, we can write down all the objects explicitly. Yeah, so our kernel now, which we have in mind, is given by the eigenfunctions. The noise is given by the eigenfunctions. The kernel is given by this explicit formula. We have the eigenvalues of discrete Laplacian. The eigenvalues are these numbers sine squared of pi z divided by L, where z is a number in this lattice. And these are the coordinates, so these are the eigenvalues of a discrete Laplacian. And it turns out that this is the covariance function, explicit representation. And the noise is given in terms of this square root of eigenvalues, which appear here, times standard normals, times eigenfunctions of a discrete Laplacian. And these are sine and cosine functions, where x and z are discrete vectors. So x and x z, this is a scalar product for this n-dimensional discrete vectors. And so this is the explicit representation of a noise. And of course, now it's really a well-defined object. There is no need to go to distributions or whatever. We can ignore this formula. And in this discrete case, it really turns out that this noise has a distribution which is given explicitly. Namely, it's the Lebesgue measure on the set of all these vertices of this lattice. Yeah, you have this lattice with partition into L points in each coordinate. So you have L to the n lattice points. And in each lattice point, you make a random variable which is distributed with respect to the Lebesgue measure. And then you scale down everything with this higher order energy. It's not the Laplace, it's not the Dirichlet energy, but it's this Panite's energy or whatever. In dimension 4, it would be the Panite's energy corresponding with a bi-Laplacian. The discrete version of it, this is now a rigorous formula in this discrete setting. And a result which we proved is that the fields given explicitly by this heuristic definition, which is now a rigorous definition, converge to the field which we have constructed before. If we test them against Sobolev functions, other possibility is for these discrete fields on these lattice points, we just make the Fourier extension because we have this Fourier basis both for the continuous Laplacian and for the discrete Laplacian. And we simply can extend every field on the discrete lattice to a function on the continuous lattice. And then this extension converges in each of these negative Sobolev spaces. And I think I'm done now. And thank you for your attention. And we have a short break, and you can start with questions already.
Thank you very much. Are there any questions from the audience? By the way, someone wrote something in the chat.
Oh, okay. I have to look.
May I just ask it directly?
Yeah, I see it now for a question. Okay. Yeah, okay. In principle, I have answered this question. So the question is whether both fields, grounded and ungrounded, are conformally invariant. And so the ungrounded field is conformally invariant without any correction. So this is in some sense indeed one of the reasons why it's nicer to work with an ungrounded field, because you don't have to care about mean values and so on. The grounded cannot be conformally invariant just by this requirement that the noise has spatial mean value zero. So, but this is a minor adaptation. So in some sense, yeah, this is a field, and this is just a constant. This is a random number. You have this field which oscillates on your manifold, and this has no spatial dependence. Yeah? You just subtract something in order that the mean value of this new guy with respect to the new measure again is zero. So in the sense of random fluctuation, it's the same object. You only have one rescaling parameter, but if you construct random measures or whatever, this is not really of relevance.
Thank you. May I just ask one short question?
Sure.
Does all of this work both on real and complex manifolds? I mean, is it applicable to real and complex settings, say even for several for higher order complex?
So we did it so far only for real manifolds. It would be too risky for me to say whether and how it extends to complex manifolds. I don't really know. So, okay. And no, I don't know. I would not. Okay, I don't know. Yes.
Okay.
Not easy to find an immediate answer. Right?
Sure.
But of course, the dimension is very important, and everything depending on. Okay, we have to check. I don't know what is known for complex manifolds.
Thank you.
A very naive question, at the risk of embarrassing myself or showing that I little I could follow. So, just to understand the big picture. So, is the idea here that if take as a starting point the Gaussian free field in 2 dimensions, we take that as something we're familiar with, then is this essentially a generalization of that to any Riemannian manifold?
Not really. In some sense, the message which we want to promote is the Gaussian free field with its Dirichlet energy. This exists. This you can construct on manifolds of every dimension. It gets worse and worse for higher dimension you have. Yeah, so in dimension 1, it is regular of order C1/2 essentially. In dimension 2, it's C0 minus epsilon. In dimension 3, it would be C minus 1/2. In dimension 4, it would be C minus 1, and so on. But it's well defined. It will be a distribution in Sobolev space of order H minus whatever, some dimension n minus 2 over 2 or something like that. This Gaussian free field exists in all dimensions and also on manifolds. This is not the object we are interested in. So the message which we wanted to promote is now that most people, of course, think energy typically is gratin squared. And our message is in higher dimension, you should go to Laplacian squared, or this is in 4 dimensions. In 8 dimension, you have Laplacian squared to the square. So you have a Laplacian to the 4 in 8 dimension as a generator. It's similar to Gaussian field, but if you think of, for instance, if you want to write down discrete approximation, whenever you have a Dirichlet energy, you always can take a triangulation, and you take these head functions. This is a discrete minimizer of a Dirichlet energy. if you have a bi-Laplacian operator, of course, it's more complicated to think how to do for interpolation. So therefore, we use for factorials for Fourier basis, because in the Fourier basis, we also can write down what does it mean we have Laplacian to the squared, things like that.
Okay, so your message is these other fields are actually nicer than the Gaussian free field in these high dimensions.
Yeah, they are more regular, and they exactly have the same borderline regularity as the Gaussian free field has in dimension 2.
Right.
What we aim for is, in some sense, this kind of borderline regularity. Not smooth and not really singular, but a little bit singular.
And so have physicists considered these other fields in the past too, or is this?
There is some work in physics literature, not that much. Only very singular contributions. To be honest, I don't remember now the name of his contributions. There is one or two works in mathematics. So Baptiste Cercle has one paper where he also studies this conformal invariance. Actually, I don't really know whether it's called. But at least he constructs similar things. And there is some work. Okay, now I remember a little bit more. There is some work in physics literature, but for instance, they did not realize that this energy could be negative. And this already gives some doubt to the rest of his work. So if you deal with these objects, of course, you have to take into account that things might be much more complicated. But it's not so in the focus of this object. These operators, which I have discussed here, this Graham chain Mason Sparling operator, this is very intensively discussed in real analysis. So people like Charles Pfefferman and so on have written several papers on that. There's a whole theory where people ask for properties of Riemann manifolds which are conformally invariant. There are spectral properties and so on. And most work for these operators comes from real analysis. Of course, there might be also physics literature which takes up these things, but the physics literature which constructs random fields based on this is quite small. It is existing, but not large.
Great. Thank you.
Maybe I take the chance to ask a question, so the other people in the audience have more time to think. So what was stopping you from dealing with odd dimensions? I didn't get that.
Sorry, once again?
So what happens at odd dimensions? So why you, I'm sorry, is it a question about technicalities, or maybe some object is not unique, or what is the case?
Okay, it's maybe both. At the moment, we don't really know what happens. We know that several things do not work in odd dimensions because the operator which we have to consider is Laplacian to the n/2, n½ power of a Laplacian. So in odd dimensions, this is a pseudo-differential operator. Now, for instance, in dimension 1 is the square root of a Laplacian, square root of a negative Laplacian. Of course, this has a kernel. It's well known, but it's a pseudo-differential operator. The Fourier analysis is very similar, but we also have formulas, and later in the presentation by Eva, you might also see some glimpses of this, where we derive things like a Girsanov formula by change of variable. And for this differential operator is much nicer if you have a change of variable and so on. And we do not have any, okay, let's say in the literature, we did not find so far the object which we needed. So the existence of this differential operator is not invented by us. So this is this Chin Sparling Marson operator. And this is extremely complicated, to be honest. And at the moment, we don't know what happens. We have a certain belief that everything depends on the kernel, not the operator, but its inverse kernel. And FIS still should have the same properties. But we have no idea to prove that. So it's just speculation. At the moment, nothing is known for odd dimensions.
Thank you very much. I think we have time for one more question.
So maybe I could ask
maybe just one,
about,
if I may.
Oh, go ahead.
So, just a very short one, maybe stupid, but can dimension be any number? This was asked by Julia. Does it have to be integer? Or can it
it has to be integer. No, at the moment, it has to be an even integer. Because we consider the Laplacian to n over 2. And we want that FIS is a differential operator and not a pseudo differential operator.
Okay, thanks.
Maybe I have a question also related to the underlying manifold. So you're always working on a compact space. So is there interest in trying to carry this out in sort of an unbounded domain, or maybe some sort of a sequence of manifolds that's sort of increasing in volume and understanding the limiting object there?
This is certainly an interesting question, and we will address this. At the moment, to be honest, I can't give you an answer whether this will be successful or not. So at least the procedure we choose will not work anymore, because we have this naive construction right now that we take the eigenbasis and each eigenfunction we multiply with one Gaussian noise. And if you enlarge more and more, this will explode. This will not lead to a limit. But in, let's say, this standard cases, flat R2, we know how to construct Gaussian field. And we have to better understand what this means. So on manifolds, it might have to do with the fact whether the manifold has, what are the ends of the manifolds? Whether they are small ends, big ends, or whatever, or the dimension of a space of harmonic functions might enter the game. But I must say, at the moment, I don't really understand how we would have to attack them. You have to factor out more functions, not just constants.
Yeah, right. Because you might have a non-constant harmonic function, so
yes,
something like this, right?
And I guess it has to do with the dimension of harmonic functions, which is n+1 in nice cases and so on. But it's a little bit on the agenda of us, but we did not start to think seriously on that problem. And for manifolds, okay, I don't know. But it's really an interesting question.
Okay, thank you.
Okay, thank you very much, Theo, for the very nice talk. And I think it's time to move to the next talk by Eva Kopfer. Hey, Eva, can you share the screen?
Yes.
Yep.
So can you see my screen?
That looks perfect.
Okay.
Thank you. So for the people who are joining, today we're having this double seminar with Theo Sturm and Eva Kopfer from University of Bonn. Now Eva will give the second talk on Liouville geometry. The floor is yours, Eva.
Thank you very much. So as a naive goal, let me explain to you the following. So let us fix an admissible manifold Mg, and we have a copolyharmonic field. And so we want to study now the induced random geometry, which we obtain by conformally changing our fixed metric G by the factor e to the power of 2 times h, where h is now this copolyharmonic Gaussian field. And so we get a new metric tensor. And so the problem which arises here is, of course, that this copolyharmonic Gaussian field is quite irregular. So we do not have a function here. So the question is, okay, what is this exponential of h? So there is no meaning of it. And so the hope would be to relax this a little bit by studying maybe a metric measure space structure instead of a Riemannian manifold structure. So if we could write down this h as a function still, then the random volume measure would be given by this new h, which is displayed here. So the weight is then, so this is the original volume times this weight given by the exponential of n times h. And on the other hand, we could construct or could consider the random metric, which comes from this tensor, which is just the distance between 2 points. And we take now the infimum over all paths joining x and y. And we consider the speed of the curve, and we weight this with this conformal factor e to the power of h of phi. Okay, so still also in this measure and also in this distance, we have a problem here because we take the exponential of something which is not a function. So one has to take care of this and one has to think about how to define this properly. And so this can be done, at least in 2 dimensions. This is understood quite well. So, okay, the first step is to replace this Gaussian field H by modifications, which are called HL here. And also you have to renormalize properly. So we will introduce, or we need a parameter gamma, and so it has been shown by Duplantier in Sheffield, or also by Roth and Vargas, that we have existence of such a measure. So this is the first step here, as the limit of something which looks quite familiar to what we can see here on the slide before. But okay, we have to introduce this gamma as in place of this n here. And also we have to renormalize by the variance of this HLs. Okay, and then they showed, and at least in 2 dimensions, that this random measure exists. So this is concerning the measure. And later, also, it has been shown that we can give meaning of this metric. So the metric can also be obtained by modifications, and we also need to rescale this properly. So this is given here by this lambda, which depends also on gamma and on L. And the point is that concerning this distance, it's much more complicated to find the precise renormalization. So it's much more complicated than in the case for the measure. And a little bit more is known in the particular case of gamma equal to square root of 8/3. So this has been found out by Miller and Sheffield. That then in this case, we have really this random metric measure space, and it is isometric in distribution to the Brownian map. And this Brownian map is the scaling limit of random triangulations. So in this case, there is much more structure known. And also in this case, you know the particular rescaling lambda. Okay, and yeah, these objects are known as, so this measure is known as the Liouville quantum gravity measure, so this limit. And the distance is known as Liouville quantum gravity metric. Okay. So our goal is now in some sense to generalize this to higher dimensions, namely where we take H to be as the previously introduced copolyharmonic field. So we have, again, as before, M is a compact manifold of even dimension. And I guess it also should be admissible. And what we can do now is that we take the finite dimensional noise approximation. So this is here given by this HL as before, where nu j are the eigenvalues of this Graham-Jen-Mason operator. And so you consider now this HL in this exponential. This is a well-defined object, and you again have to subtract this variance term. And what we get then is for sufficiently small values of gamma. So we also need this, have needed this before in this results for the two-dimensional case. So if gamma is smaller than the square root of 2 times n, then one can show that there exists a random measure mu such that these finite dimensional approximations converge. So more precisely, this means that if we test against a continuous function u on the manifold, and we integrate this with respect to this mu L, and so this is a random number, and this converges then to this integral u against mu in for almost every omega, so p almost surely as L goes to infinity. And yeah, this random measure is then called the Liouville quantum gravity measure as before. So here we have, in some sense, the L1 statement. This next slide, we see the L2 statement. So if we have L2 and we consider the continuous bounded function tested against this approximation, then one can show if gamma is a little bit better, namely it's smaller than square root of n, then this is a two-bounded martingale. And in this calculation, one sees where this critical case pops up. So this logarithmic divergence. So if we compute now the supremum of the exponential of YL squared, and so we insert what this is by just taking this definition, so taking the integral squared, and okay, we will see that we end up here with by taking the expectation that we end up here with this double integral of e to the power gamma squared KL, and okay, so but this can be estimated above just by taking the k, yeah, because we leave out these other these other terms which are non-negative, and okay, and then we use this logarithmic divergence, and then you see okay that this latter integral is finite if and only if gamma squared is smaller than n. And similarly, this works for the L1 case, but then you can also allow for larger values of gamma. So what you can also show is then that if gamma is smaller than square root of 2, then we have that this constructed measure does not charge sets of vanishing H1 capacity. And what this means is that the Dirichlet form, which we now consider on this measure, on this L2 space with not with the volume, but with the Liouville quantum gravity measure, that this is a regular form, Dirichlet form, and we can construct then a Liouville Brownian motion. And this is just a random time change of the usual Brownian motion. So this has been also known in 2 dimensions. This has been done, for example, by Nathaniel Berestiki. And moreover, we obtain this invariance, so quasi-invariance under conformal transformation of this Liouville quantum gravity measure. So if we have Liouville quantum gravity measure on a fixed manifold, and we consider now the conformal change of the metric tensor and consider the associated Liouville quantum gravity measure, then we can say what this new measure looks like. And namely, this is an explicit factor, which we can see here, times the original Liouville quantum gravity measure. And so these quantities which are depicted here are explicit. And so, okay, so we constructed this Liouville quantum gravity measure with a finite noise approximation as before, with the co-polyharmonic field. But we can also consider this discrete approximation. This has been also done has been set by Theo, and we can also use this for the Liouville quantum gravity measure. So if in the particular case, if M is the continuous torus, and we consider this standard mesh with length 1/L on this torus, then okay, we had this discrete polyharmonic Gaussian field by taking the discrete eigenvalues of the discrete, so the eigenvalues of the discrete Laplacian on this mesh. And here we have the standard IID Gaussian variables, and here we have this Fourier basis. Then we can associate now a discrete Liouville quantum gravity measure to this mu L. By just inserting this discrete copolyharmonic Gaussian field. And ML here is just the normalized counting measure on the grid. And what we get then is now, in accordance to this approximation of the copolyharmonic fields, we have also convergence of this discrete Liouville quantum gravity measure to the continuous version. So this is this next theorem here. What we need here, for the first statement, so if we just take this discrete Liouville quantum gravity measure, so when we take the piecewise constant extension of it, then we have that this converges in law as L goes to infinity, and we have here gamma is smaller than square root of n. So this is a little bit worse than the result before. And the reason for this is, in some sense, that we take so we have here now in this approximation these lambdas, and these lambdas are the eigenvalues of the discrete Laplacian and not of the continuous Laplacian. If we want to get a better result, this is the third assertion in the theorem. So here we get the original range of gamma. Then we can take the so-called spectrally reduced semi-discrete Liouville quantum gravity measure, and this consists just as by taking the associated Liouville quantum gravity measure with replacing these eigenvalues of the discrete Laplacian with the continuous version. Yeah, and also we have here another statement. I mean, you can also extend this measure just by taking the Fourier basis, by not taking just the Fourier basis at these grid points, but just I mean, these are everywhere defined, and then you can extend this measure by taking just the Fourier basis at these other values, and but then we also have even worse, that gamma is smaller than square root of n, and divided by e, so by the Euler constant.
Excuse me, may I interrupt? Yeah. Naive question. So these measures, the LQG and the approximation, these are random measures, correct?
Yes.
So I think I understand what it means for them to converge in law as random variables, measure valued random variables, but what does it mean to converge in law in L1?
Okay, I guess so. This is what is meant by this is this statement. So you test against a function, and then you have a random number, and then you can say, okay, this random number converges in that one.
Okay, in that sense, good. Thank you.
Yeah, thanks. Okay, so this was about the Liouville crunch and gravity measure. So on the next, in the rest of the talk, I want to talk about this Polyakov-Liouville measure, so which I introduced now, or I will motivate this now. So this is also motivated pretty much from two-dimensional theory. So again, we consider this conformal change of an original metric, and this conformal change is given by the exponential of a parameter gamma times h. And so here for the beginning, let's say that as always, okay, G is a smooth reference metric on some fixed two-dimensional surface now, because we are in 2 dimensions. And H is now, for simplicity, so for the starting point here, a smooth function. Then what we have here displayed is the Liouville action functional. And this is given by this formula. So so this looks familiar. So this is this first term here is just the Dirichlet energy of H. So we had this before. And now we add 2 other quantities. So this second quantity here is, on the one hand, we have a parameter here, and this Rg is the scalar curvature. So on the surface, this is just the Gauss curvature times h. And here we also have a reweighting of the manifold, so by this exponential of gamma h and times the parameter m. So m is also just a parameter. And we integrate this on the manifold. So what one gets out of this is that if you consider the Euler-Lagrange equation of this functional, that these satisfy the classical Liouville equation. So the Gauss curvature of the conformal changed metric is of constant negative curvature. And this constant negative curvature is given by this -1/2 times m times gamma squared. Okay, so minimizers of this action functional produce metrics with constant negative curvature, so which is quite interesting. And now you can formulate this in a probabilistic way, similar as before. So we take this Liouville action, and so minus the Liouville action, and we take the exponential, and we integrate with h, which is non-existing, right? And as before, this does not exist. So this is a formal way of writing this, and z is again a normalization constant. And this formal definition, this goes back to the seminal paper by Polyakov from 1981. And this has been made rigorous by David Kopyainen, Roth, and Vargas in 2016. Okay, so the goal is now to get an idea of this measure. So this measure here is called the Polyakov-Liouville measure, and the goal is now to transfer this to higher dimensions by again considering h, random fields h, which are given by the copolyharmonic Gaussian field as before. Then what is the ansatz? The ansatz is depicted here. So okay, so we have again SG, and we want to define this by the following. So the first term here, this should substitute the Dirichlet energy, and for this we just take this associated Graham-Mason-Sparling energy. So this is this first term here. So PG is here the copolyharmonic operator. And then the second term, this should replace this Gauss curvature term. And here we do not take the scalar curvature, we take Branson's Q curvature. I will say something about this a little bit later. Here we allow for another parameter. So here we have just a parameter divided by the volume of m times the field. And okay, this stays the same. So this is still n times e to the exponential, exponential of gamma times h. Yeah, so as I said, so PG is the copolyharmonic operator and Q is the Branson's Q curvature. So as we have seen, this copolyharmonic operator is conformally invariant operator. And this is also the reason in some sense why we want to move from the Gauss curvature to from the scalar curvature to the Branson's Q curvature, because the total Branson's Q curvature is also conformally invariant. But the scalar curvature is not conformally invariant in higher dimension. It's only conformally invariant in dimension 2. So at least the total curvature. So, and this Branson's Q curvature, for example, so in 2 dimension, it is exactly 1/2 times the Gauss curvature or scalar curvature. And in 4 dimensions, okay, it gets a little bit complicated. So what we have here is Ricci squared, and here we have the Laplacian of the scalar curvature, and here we have the scalar curvature squared. So you see it, it's getting complicated. But the crucial point in some sense is that its total Q curvature is conformally invariant. So if we integrate it out the manifold with respect to the volume. And okay, we know more. So if we have a conformal change of a metric, then we can compute this new Q curvature, and this is the formula we get then. So we have here the weight exponential of n times phi of this new Branson's Q curvature, and this is just the old Q curvature plus this renormalization times the copolyharmonic operator. So this is the formula one gets out of this. So what is interesting about this? Yeah, if we, as before, so before we found this classical Liouville equation. So what do we get for minimizers here? So minimizers, so if you consider the Euler-Lagrange, satisfy this equation here. And if we choose now theta star equals to 0, and yeah, so we choose the constant in some way, then we will find a little bit, so it's a formula which looks nicer. So this is depicted here. And if we recall our conformal change law of the Q curvature, so we will find that this term here on the right-hand side pops up here. So this is exactly the new conformal, the new Q curvature, so under the conformal change. So in other words, we have that this conformal change, so this metric we get is of constant Q curvature. So this is now in some sense the generalized version of this classical Liouville equation in terms of this Branson's Q curvature. Okay, so then again, so we want to have a probabilistic expression of this Liouville action. And so informally, so this is again, we take this action and we take the minus and the exponential, and we want to integrate this in h, which is not possible, but we can do this rigorous by considering the objects we already defined. So I mean, this exponential of this minus times this first operator here integrated with h, this should be now the law of the conformally invariant Gaussian distribution. So this is the law of this copolyharmonic Gaussian fields. So this is this integration here is this first expression in this informal ansatz, and yeah, then these two do not trouble us so much because we can just test them against each other. And then we still have here this n times exponential, and this is just the Liouville, the Liouville quantum gravity measure, which we defined previously. So the associated Liouville quantum gravity measure of H. So this has been constructed already by Sackley in 2019 for even dimensional spheres. And we have constructed this for general admissible manifolds then, so together with Lorenzo dello Schiavo and Renaud Herry in 2021. Okay, so here we have once again the rigorous expression of this Polyakov. So this is now the named Polyakov-Liouville measure. And okay, one is quite often interested, when is this finite measure, so that we can renormalize it and get a probability measure. And this is the case if we have that gamma is between 0 and square root of 2n. And we have the total Q curvature times theta plus theta star is negative. We also have some sense conformal quasi-invariant structure modulo shift. So this is this theorem here. So the Z is the conformal anomaly, and T is as a shift of this of the original Polyakov-Liouville measure. So in some sense, this is Yazanov theorem. And this has been already also predicted by the physicists without having the rigorous formula. It's also like for the Wiener measure, you can also predict Yazanov without having a rigorous definition, but only using this informal definition with the integration over this non-existent uniform measure. Okay, so now in the last minutes, I want to tell you something about the semi-classical limit. So for this, let us first go to the two-dimensional case where we know more. So in the 2 dimensions, Lacoin, Roth, and Vargas, a few years ago, I think it's not so old, study semi-classical limit of gamma h. So what does this mean? So we let gamma go to 0 and let m go to infinity. So m was this, this object here. So this mass, which is multiplied by e to the gamma times h. So we let this go to infinity. With the condition that we have that n times gamma squared is fixed. And what they can show is that at least for flat metrics, that these fields, we divide here by 2 just because of our formulas we have here, times h converge in law towards the solution of the classical Liouville equation. So this equation here, where we have constant negative scalar curvature. And also they show that the fluctuations around this hyperbolic geometry is given by a massive Gaussian free field with mass proportional to this lambda. Okay, and this is a quite interesting result that you get from this probabilistic approach, this classical Liouville equation back, and also by a large deviation principle. And it would be interesting, so this is more like, and so we do not have a solution for this right now, but it would be interesting to study this also in arbitrary dimensions. So we one could consider the semi-classical limit of this gamma divided by n times h, and show that this concentrates on the set of minimizers of this Polyakov-Liouville action in higher dimensions. And these minimizers, as we have seen, are characterized by as solutions of this Euler-Lagrange equation, which we had already before. And if one has this, then again, according to this transformation formula of the Graham-Jen-Mason-Sparling operator, and for the Q curvature, this, or what is depicted here, is equivalent to saying that the Q curvature of the conformal changed metric is equal to minus lambda. Just by considering this conformal changed formula, that's so the formula for the conformally changed objects, and this means that the three-scale Polyakov-Liouville measure concentrates on the set of these conformal weights which lead to manifolds of constant Q curvature. So instead of in 2 dimensions this constant scalar curvature, we have constant Q curvature, constant negative Q curvature. Okay, so I want to stop here with this outlook, and thanks for your attention.
Thank you very much, Eva, for the nice talk. Are there any questions?
Yeah, I have a question again. Most of the results that you presented were about the construction of the associated measure. So, like, think about the Liouville quantum gravity measure. But at the beginning, there was this result in 2 dimensions that also gave the construction of the metric. Perhaps I missed it, but do you have a result also about this,
No.
the construction of the metric in higher dimensions?
Yes, so we do not have, but there's a very recent paper by Wynn and, okay, I have to lie about the second author, which generalizes this 2-dimensional results to higher dimensions, at least
Okay.
for the for the Euclidean spaces. Yeah. But
Okay,
it's
okay.
not known
flat
for
space,
manifolds.
yeah. Mm-hmm.
And we have not yet considered this. Yeah.
Mm-hmm. Mm-hmm. But like their direct approach, say in 2 dimensions of Wynn and Miller, for example, doesn't directly apply to higher dimensional manifolds.
Yeah, right. So this metric is a much more complicated object than this measure. So this already appears in this renormalization. So also in 2 dimension, I guess this renormalization is only known. So the specific value is only known for the square root of 8 divided by 3. So one can imagine that. So this is much more complicated than this measure. So this was, in some sense, our first goal to generalize the result for the measure.
Okay, thank you.
Maybe I can ask also, you have mentioned physicists predicting some formulas and so on.
Yes.
Which makes me wonder, where does this pop up in physics? I mean, there's the name in quantum gravity there. It's probably a hint, but in a few words, like, where does this pop up in physics?
Okay. So, yeah, this Liouville, this Polyakov-Liouville measure, this pops up in physics, so in conformal field theory, and yeah, so it's some form of quantization of a physicist's object, but and I think they are pretty much interested in this conformal anomaly, which you find here in this this theorem, and they have. So I think in the paper of Polyakov, they have foreseen this, and but without having the rigorous formula.
And you have a formula for this.
Yes. So I mean, we have also a rigorous formula for the Polyakov-Liouville measure, which they have not. So they have this. I mean, they have this in some sense this informal. Where is it? Yeah, this informal expression here, where you integrate with respect to the uniform measure overall H. I mean, this does not make sense, right? So you have to come up with this. So you have to use this. You have to use this law of this copolymer, of the Gaussian, and also you have to use this Liouville quantum gravity measure. Yeah.
Thank you.
Have notion. Yeah.
A few questions.
Yeah.
Thanks. It was a great presentation, but just 3, I think, questions. Firstly, you discussed naturally random surfaces like Liouville quantum gravity. Is there any relationship? I mean, could this be translated also to SLE, like random curves? So Schramm-Loebner evolution. Does it has any application also here, and also any other measure that could be used here, possibly, instead of Liouville-Polyakov? And about the numbers that you have shown, say for gamma, we know those numbers, square root 8 divided by 3, but is this applicable to any gamma in principle, and is this related also to the kappa parameter in SLE curves? Thanks.
Oh, these are a lot of questions at once. So for this SLE stuff, I have to say I cannot say anything reasonable at the moment. I'm sorry to say that.
Yeah, sure. It's
but I guess every question was somehow related to this, right? Maybe I forgot one.
Also about this gamma, can this be applicable? I mean, the thresholds that you have shown, I think, were only for gamma, which is always lower than some number. Is this extendable to any gamma in this case?
You mean, for example, convergence of this?
Yes. Or in general.
Yeah, I think the point is also that you want to have a non-trivial limit object. So if you extend this, so you want really to have a measure and not something which is a constant zero or something like that. So I think this is really the optimal range. So this square root of 2n is the optimal range.
Okay, thank you. Thanks.
Maybe I can add some words. This is of course correct what Eva said with a maximal range, which is for the measure gamma less than 2. But maybe your question was also concerning the square root of 8/3. The square root of 8/3. This is the only case where this rescaling parameter is explicitly known. So what these groups have proven is there exists such a parameter, but only in one case this is known explicitly. In other cases, this is not known. And this has to do, roughly speaking, with the fact that this measure and this metric are related to each other. And in this particular case, we know that the Hausdorff dimension is 4. Now you are in a 2-dimensional space, but for this value, we know the relation. And this rescaling parameter has to do with the question, what is the intrinsic dimension of this metric measure space? Because naively, you scale distances with a factor 1 and volumes with a factor 1 times Hausdorff dimension. But this Hausdorff dimension, or this dimension, is not known explicitly, only in one case. And concerning this question with the SLE plays not so much role with these objects. There is a relation for certain values of gamma and kappa that the level sets of his random fields are SLE curves. But you also have to make this more specific because these fields are not functions. So also it's not really clear what means level sets or level lines. But you can make this precise for certain parameters, and then you obtain SLE curves or SL loops. But this is not used for the construction of a random gravity measure. So it's just that these two theories are related, but here in our approach, we do not benefit anything from knowledge of SLE.
Okay, thank you.
Okay, are there any more questions? Yes, I think we can stop here. There's been already many questions in these two sessions, and we would like to thank you, Theo and Eva, very much for the very nice talks, very interesting and very impressive works. Thank you so much. And yeah, we meet again in 2 weeks for the next session of this seminar. Okay. Good.
Thank you.
Thank you, everybody. Ciao.